Hello and welcome to another Monday Night Calculus. I am your host, Curtis Brown, and I have got Steve Kokoska and Tom Dick here and Allison running the shots in the background. We sure appreciate everything that she does to make these evenings happen. Steve, it's been a little while, but I'm really excited to see you. I'm excited to see the questions that have come in and the things that you have. Before I let you get started, I want to make sure that everyone knows that we will be again watching the chat this evening, and one lucky participant this evening is going to be given a chance to have a session led by you and Tom, ready for one of their classes at school. Of course, we'll be doing it remotely. We won't actually be showing up at your school, but someone this evening, a busy person in the chat, will get a chance to have Steve and Tom teach a course for them, a class for them, sometime in the near future. So we'll be talking about how that works here toward the end. Go ahead, Steve, and take it away.
Thank you very much, Curtis. Let's see if I can get this to work. There we go, sharing my screen. Hope you can see that. Terrific. Thank you for everything, Curtis. Allison in the background. Tom, great to see you again. And by the way, that class was a lot of fun. Curtis, thank you for arranging that. I hope we can.
Absolutely. Yeah, we did that a couple of weeks ago, and that was a lot of fun.
It was a blast. There were an awful lot. There was a flurry of questions on the Facebook page this week, and I've done my best here. I've collected, I think, 4 of them. And one of them I put together as you prepare your students for the AP exam, sort of a free response question that has to do with area and volume. So let's start out by taking a look at this one. This is a nice question to start out with. It has to do with the fundamental theorem of calculus part 1. And it's got just a little bit of a twist in it. And I'll show you how I would solve this one. And we'll even get some graphical confirmation in this, I hope. So in this particular problem, we have g of x defined as a function, and it's got a definite integral in it. And you'll notice up here that this upper bound is not just x, but rather x squared. So we've got to be careful when we apply the fundamental theorem of calculus. We want to find the value of g prime of 2. And just as sort of an aside, sometimes when students see a problem like this and they're asked to find g prime, one of the things they try to do often is to actually find a symbolic antiderivative. And that's not easy on this particular problem, if at all. And generally, if you have one like this on the AP exam, they're going to give you an integrand where you can't find a nice antiderivative. So, okay. How do we start out by finding this derivative? Well, I'm going to use the fundamental theorem of calculus, but I've got to use the chain rule here. So I'm going to start out by letting u be equal to x squared. So I want to take the derivative of this function with u with respect to x, with u as the upper bound, recognizing that u is a function of x, and applying the chain rule. I start at the outside and work my way in. I take the derivative with respect to u of the outer function and multiply by the derivative of u with respect to x. Now, if I've done everything correctly here, let's see. Using the fundamental theorem of calculus, we would simply plug in, everywhere we see a t, we're going to plug in a u. We still need to find the derivative of u with respect to x. In this next step, let's see, I let u be equal to x squared. Did I do that right? 3x squared, x squared cubed, so x to the 6 plus 1. There's the derivative of u with respect to x, and I did a little bit of simplifying. Now, I'm not done. I've sort of combined everything or written this conclusion here. I have g prime of x equal to this rational expression, and I was asked in this problem to find g prime of 2. So I plugged in an x equal 2, and I did a little bit of simplification, and I got a 48 divided by 65. That's a nice question. And you know me, Curtis, I like to back things up, confirm things graphically if I can, and there's a nice question for the chat, if we can get this in here. I'm using Mathematica, and Tom will have to help me on this one, but I think maybe even using the TI-Nspire, maybe even the TI-84, you can actually produce a graph of g of x. Remember that g is defined with a definite integral. So this blue graph right here is a graph of y equal g of x. So I computed g of 2, and I drew the tangent line to the graph of g at 2. And this is looking pretty good to me. That's got a slope, let's see as I look at that, well, a little bit less than 1, I guess, okay? So I'm going to say that m here is 48 over 65. It's at least positive. It's a little bit less than 1. I'm feeling pretty good about this answer. Now, one characteristic, we'll go a little bit further here. Curtis, I'm going to test you on this one. Do you see any characteristic, any kind of simple characteristic for this function g, the way that it's drawn? Can you describe anything in there? Not increasing or decreasing or anything like that. Not that complicated, but do you see a nice characteristic in there?
Where it's positive when x is greater than 1. I'm not sure what you're looking for.
Well, let's see. Do you see anything with respect to the y-axis? Seems like I could kind of fold it over that y-axis.
Oh, it does. It does appear pretty symmetric. Yeah,
it does indeed.
I got you.
And therefore, what kind of a function is this?
I would call it even.
You betcha. So it certainly looks like, very good. It certainly looks like g is an even function. And I would suggest that this is a little bit different, sort of an even function, and one that we don't often ask our students to try. You know, sometimes we define even functions, we define odd functions, and okay, we give them functions, polynomials, and sometimes there's a trig function in there. But this one has a definite integral. I wonder if you can show that this function is even. We'll leave that as an open question. Tom, do you have any technology on this one?
Yeah, I do.
Okay.
So,
all right. I will stop sharing.
You actually brought up the question, Steve, about whether or not you could graph this on the Nspire or the TI-84. And
Yes.
the answer is you can actually do either one. So
Okay.
I think what I'm going to do is actually illustrate it on the 84.
Okay.
So I'll share my screen and try to fire up the 84, and you guys can give me some feedback if you're seeing that okay on your.
Got it.
Yep, looks good.
Okay, fantastic. Okay, great. So I'm just going to go to the y equals, and I went ahead and took a little bit of time right before we got together to go ahead and enter that that function as it was given on Steve's summary sheet there. So there's that integral from 1 to x squared, 3 times t over t cubed plus 1, and we're integrating with respect to t. I want to just take a look at the graph of this. So this is, TI-84 is not a CAS machine, but what it's going to do is for each value of x, it's going to actually numerically approximate this definite integral and plot that point. So for every pixel across the screen, it's computing this complicated definite integral. Let's take a look at how it does. So I'm going to hit graph. And if you're wondering about the speed of the graphing, just keep in mind that every single dot that's being computed is itself this definite integral, or it had to plug in a value of x and do that numerical value. So I think it'll actually look like it'll speed up here pretty soon. It's kind of, it may be illusory. I think it's because the slope is steeper. Oh, it's picking up steam. It's like it's going downhill. It could go faster.
I think this is a really
I think
this is a really cool point that you're making here, that the 84 is in fact calculating that definite integral every single time, right?
Yes. Every single time. And it's not using antiderivatives. It's actually doing a numerical.
Right. It's computing this. Numerically every single time. And just the fact that you can do that on the 84, I think, is something that a lot of folks maybe aren't aware of, and certainly makes things pretty cool here on this picture.
Yeah. I think that's been my experiences. A lot of people are actually surprised until they actually see it do it. But yeah, you can definitely graph these definite integral functions. That's what I call them, the ones where you have the variable as one of the limits of integration on 84, just like you can any other function. So it's kind of cool. So I did want to do kind of a reality check similar to what Steve did graphically. This will be a little bit different. I'm going to go ahead and pull up the trace and trace along this curve until I get to x equals 2. Okay, there we are. And the reality check here, Steve actually drew in a tangent line. I'm just going to calculate what's the slope of this curve at this point. Okay, so I'm going to pull up the calc menu. These are the things in your graphics environment that you can calculate off a function graph. And we look down there at number 6 is dy dx. That's going to give us the slope at that point. So I'll enter 6, and we're right there at x equal 2. So let me just go ahead and hit enter. And it's giving me the value of the slope down there at the bottom. You can see it's 0.738 and some change here. Now, Steve came up with this nice rational number, so I'm going to try to keep that in mind at 0.7384. Let me just quit off of the calculator screen, or excuse me, the graph screen, and I'm going to put in 48 over 65 and see what that number looks like.
Pretty good.
Oh, looks pretty nice to me. Okay, so we're getting, and so that chain rule, the easiest thing to forget on this kind of fundamental theorem of calculus example that Steve showed is forgetting the chain rule. You know, if you've got a function up there in the upper limit, is remember the chain rule is always in effect when we're differentiating any kind of function. And so getting that extra factor of 2x into the picture. All right, I think I'll stop there and let me see if I can stop the share here real quick.
So while we're transitioning back over to Steve, I just want to put out one more little plug here. So just a heads up for those who've joined, maybe joined a little bit late. So again, this week we are going to be giving away a session with Steve and Tom. They'll come do this remotely, teach a class for you at your school. So we'll do that remotely. They'll teach one of your calculus courses. That would be, we did it last month. And it was a lot of fun. We had a great way to kind of interact with the students, and it was a good time. The way you can do that or get participate in that is participating in the chat here tonight. So we'll be selecting from someone who's posting questions and comments and things in the chat. So just a heads up.
Very good. Well, this is a good question too. This involves solving a differential equation. And I'm kind of grateful for Michelle Owen for posting this one on Facebook for a couple of reasons. There were several posts after this one involving initial value problems. So there's a lot of questions surrounding this kind of a problem. And it also made me remember fondly a professor that Tom and I had in graduate school, Shepley Ross. I wish he were here to help us answer some of these questions, Tom. But I think I got some of it figured out. We may disagree a little bit, but let's see where this goes, okay? So, all right, the only kind of differential equation that the AP program will ask our students to solve is one that is separable, and indeed this one is. So I'm going to start by separating the variables. So I'm in this step right here. I've got all my y's on one side and all my x's on the other. So my next step now is to take the antiderivative or find an antiderivative on both sides. I often get asked the question, well, look, do I have to put a plus c on both sides and then combine them? No, you don't have to do that. You can just automatically put 1 plus c on one side of the equation. I tend to put that on the side with the x's, but that's just me. It doesn't have to go there. You will notice here that when I took the antiderivative of both sides, these natural logs do indeed include an absolute value symbol. And I would caution or suggest that you remind your students to do that, because in kind of a global sense here, we don't know what branch of the solution we have, or the solution or a solution curve. More on that in a second. Now, one of the questions that popped up quite a bit on Facebook was, well, once you find the antiderivatives, when do you use the initial condition? When do you solve for y? Should I solve for y right away? And I think we always suggest that as soon as you take the antiderivatives, use the initial condition. So I'm going to plug in, I think it was, looking up at the top here a little bit, I think it was x equals 0, and I think it was y equal 1. Now, a couple of things that I notice when I do this. When I plug in this x equals 0, I notice that what's inside here, the argument on this absolute value is positive. So that says to me that I am on a branch of the solution where the argument of that log is positive. So I don't need the absolute value symbols there. When I plug in a y equal 1 over here, similarly, this argument, this is a cool problem. That argument is also positive. I am on the branch or a part of the solution, or I have a solution where that argument is positive. I don't need those absolute values. So I solve for c, there it is, log 3. I'm going to go back here and write these two log expressions without the absolute value symbols. And I'm going to do a little solving here for y. Let's see, how did I go from this step to this step? Well, I think a property of logarithms, and then I exponentiate both sides. And son of a gun, the solution to this differential equation is simply the equation of a straight line, y equals 3x plus 1. Now, we often get asked about, well, what's the domain here? Now, I'm going to argue that the domain is x greater than minus 1. And I'm going to argue for that because this argument inside the log must be positive. And the only way that can happen is if x is greater than minus 1. So whatever the curve, the solution curve looks like, and we'll get there, the domain here is x greater than minus 1. Oh, well, all right, let me put a little bit of this together. If it's a straight line, it is that part of the straight line where x is greater than minus 1. Now, I think it's true, and Mark Corrali can probably correct me if I'm wrong, but I don't think we've had a question on the AP free response portion in a while that has asked specifically for the domain. And that may be because there are, not confusion, but I think people talk about what the domain of a solution to a DE could be a little differently. But here's how I'm going to attack this or resolve this. Several years ago, there was an article written by Larry Riddle, who is a former chief reader, and I think he wrote this at the request of the College Board. And it was titled The Domain of Solutions to Differential Equations. And I've extracted a paragraph out of here, and I'm going to go into this in a little bit more detail in a second, but this is the paragraph that I live by. So the domain of a solution, a particular solution to a DE, is the largest open interval containing the initial value on which the solution satisfies the DE. And okay, this is sometimes called an interval of definition or the maximum interval of existence. So why does it have to be an open interval? Well, let's just think geometrically for a minute. If I'm reading the Facebook page correctly, many instructors, many teachers are now talking about slope fields and teaching slope fields. So imagine a slope field, and I have the initial condition on that slope field, and now I'm going to use that slope field to sketch in my solution curve. I'm almost 100% sure that you would tell your students, don't draw it across anything that looks like a vertical asymptote. Don't draw it across anything where it looks like the function is not defined, where there is no tangent line. That suggests to me that you can't jump across geometrically, that you can't jump across and define the solution to a DE as a piecewise defined function. Okay. So why are domains open intervals? Well, another way to think about this is, well, look, we have a differential equation and we want a solution. That means the solution must be differentiable. It must therefore be continuous. And so we don't want it jumping over. We don't want to have a point of discontinuity. We have to be able to draw the graph without lifting its pencil. Well, okay. And here's one more quote. I found this one. It said, this is a more practical reason, I guess. It says an explicit solution of an ordinary differential equation, in order to be meaningful and useful in the real world, to have practical applications, must be defined on an open interval or on an interval. So that's a nice problem. There's lots of things going on in there. There's a piece of that where we have to worry about that log of the absolute value. And let me try to put all of this together graphically. Let's see what this slope field looks like. There it is. And I've drawn in this slope field to the right of -1, x greater than -1. And let's see if you can see this, Curtis. I've got the initial condition right there at x equals 0, y equal 1. And you know, that's a pretty good slope field. I think indeed I could. See, I think I could draw that solution curve by following those line segments. That's pretty good. And if I've done everything correctly, it might be kind of hard to see. But remember I said domain greater than -1. There is an open circle down there. And maybe you could think about why that's true. Why does there have to be an open circle there? Well, okay, I want the domain to be an open interval, but can you see in any other way? So lots of little things going on in there. Tom, anything on the calculator with that one?
Sure, Steve. I'll go ahead and kind of switch platforms here and look at the Nspire now.
So two things here. Real quick before you're switching, while you're switching, Tom. One is that earlier, Steve, you asked how long it's been, and yes. Mark responded that it's been since the Dark Ages, since before you were chief reader. So that's been a little while. And then secondly, Tom, when you get done showing this on the Nspire, could you also jump back over to the 84 and really briefly run back over that graphing of the antiderivative? We had a question about the t that you were using, and I think I answered the question wrong. So I'd like you to talk about how you got that t in there.
Oh, sure. Okay. Remind me if I forget to do that, Curtis.
Sure.
I'll be happy to do that. Okay. So can you tell me, are we looking at the Nspire here? Is that showing up okay? Great. Okay. So I've just got opened up a blank graphics screen. And so I'm going to go over to my menu and get over to Graph Entry Edit. And for slope fields and solutions to differential equations, we want to go to the differential equation plotter. So you're not going to see on this menu slope fields, but that's going to be the differential equation plotter. Okay. And we see that it's got the prime there is kind of a lot of space there, but that's a y1 prime equals. And so this is where I want to put in the expression for dy dx. And I think on entering this on the Nspire, the thing that people can sometimes get tripped up on is, notice I'm referring to the function as y1. So any place you see a reference to y in the differential equation that you're given, you're going to want to use this name, y1. So Steve's differential equation, let's get the parentheses. I think it was y plus 2 in the numerator.
Right.
What I'm going to want to type in is y1 plus 2. Mm-hmm. Okay. And then we're going to divide that by the denominator was just x plus 1. Oops, I got the wrong kind of parentheses there. All right, let me try that again. Okay, so x plus 1. And if I just go ahead and hit enter here, we should see just the slope field for this. Okay, here we go. And if you take a look at this, this is quite a bit coarser. I mean, the lattice is a little bit more crude than the one that Steve generated on his package. This is something, though, that we can control. I'm going to bring up the differential equation again. I'm going to go over here to see this dot, 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 says edit parameters. And one of the things we can choose is the field resolution. And this basically says how fine our slope field will be, how many lattice points. Now here they've got field resolution of 14. I'm just going to double that to 28 just for grins and see what happens when we plot it again. Okay. Now we're getting something that's looking a bit more like what Steve had in terms of, you know, how fine it is. Now we'd like to plot a solution to this. Now, Steve actually worked out using separation of variables and, you know, solving for the constant. He came up with an explicit analytic solution. We're going to find a solution here just following the slope field using that initial condition. So I'm going to come back to my differential equation, and down here it has x naught, y1 naught. That's a place where we can put in an initial condition. I think our initial condition was 0, 1.
Right.
Okay, so I'm going to put in 0 and 1. And it's going to use, actually, we have a choice. This one I noticed when we were in the parameters, I said Euler. It's going to actually use Euler's method. I think in the future Monday Night Calculus, Steve and I will be talking a bit more about Euler's method. But let's just see what kind of curve we get here.
Pretty cool.
Yes, it's very cool. And, you know, I was actually a little bit surprised. Notice that Euler's method, when you're doing Euler's method by hand, you tend to move just one direction forward from the initial condition. But here, notice my initial condition, 0, 1, it actually drew this both forwards and backwards. And the thing I was a little bit braced for is Euler's method, sometimes it will step over an asymptote. You know, so Steve was on the lookout for that, is that our domain really needs to be, if we want continuity and differentiability for a solution, we got to restrict the x's to be greater than -1. And here it did stop. And my suspicion is it may have stopped because we actually hit right on that discontinuity or the place where it was undefined. So it said, oh, I'm not moving any further than to the left from that. But I have seen ones where it's just using this Euler's method. You will see some kind of funny behavior because it's stepping over discontinuities. And so that's a nice picture of that. And I think that's just one I wanted to show. It's a really nice straight line. By the way, that's called, this curve is moving along slope segments that all have the same slope. And there's a technical name. It's not part of the AP vocabulary, but it's called an isocline. Cline means slope, iso means same. So a curve that goes through points where your slope field all has the same slope is called an isocline. This is an example of one of those. Just a tidbit there. Okay, so let me see if I can stop my share here.
Or you want to go back to the 84 for a minute?
Yes, I do. So to do that, let's see, to stop share the quick way that, oops. Hey, can one of you remind me what I do there? Do I need to go back to Zoom?
Way up at the top?
Yeah, I've gone to the top. But here I'm in Nspire. Do I need to go back to the Zoom program? Let's see.
Should be.
Yeah, you can go back to the Zoom program and grab that where it says share screen, and then just switch the window that you're sharing.
Yeah,
So
I'm having trouble getting
84.
back to that screen. My apologies here. Let's see. Okay.
Can I grab it?
Can
I grab it, Curtis?
Yeah,
All right.
we'll just there we go.
Yeah, you were able to do it, Steve. Thank you.
There you go. So Steve,
I'm gonna
just
share
go
screen
ahead
again
and then
and-
we'll pick up that 84 thing at the end, Tom.
Okay.
Okay. All right.
All right, this problem was posted by Nick Bennett, and this is a nice problem that involves particle motion. We haven't seen too many of those on the Facebook page, at least I haven't. And it's got a kind of a nice twist in here, a nice AP calculus twist in here, because it's got this extra sort of variable. A is a positive constant. So we have a particle moving along the x-axis, so that any time t greater than or equal to 0, so we've got a domain here. Its position is given by this function. Here it is, x of t. And we're told that a is a positive constant. And we want to know at what time is the particle's position farthest to the right. Well, all right, in order to answer this question, I've got to find the first derivative. I've got to take a look at the velocity. And here's how I would attack this one. I've got to take the derivative of this using the product rule. So derivative of t times e to the minus at plus t times the derivative of that second function. We've got to take the derivative of what's up top. There's the minus a. I did a little bit of simplifying. And when I do these problems, this is just my way of doing them. I like to try to factor completely. And I think I've done that. One might want to take out a minus 1 out of this, what's inside here, but I'm going to leave it like that for now. So one thing I noticed right off the bat here is that this expression, e to the minus at, is always greater than 0. How do I make the velocity equal to 0? Well, only if one of the factors is 0, and this is always non-zero, always positive. So the only way I can make this product 0 is if this is 0, okay? So I'm going to set that expression equal to 0. I'm going to solve for t. I've got t equal to 1 divided by a. So I'm looking for these critical points. I'm looking for possible places where the particle could turn around, where it could change direction. I have to make sure I check, are there any places where the velocity does not exist? And there aren't any. Again, t is greater than or equal to 0. We're not dividing by 0 anywhere. We don't have to worry about that. So I'm going to draw a sign chart. Now remember, sign charts are not sufficient justification, but I still think this is a very nice mathematical tool and a nice way to communicate, a nice way to see visually what's going on. And then what I can do is write a sentence to interpret that sign chart. So the way that I do this one is, since the domain is t greater than or equal to 0, it might be a little tricky to see, but I've got a square bracket, a square left bracket in there, so that my domain is t greater than 0. I've got a tick mark at the only place I need to worry about here, where v of t is equal to 0, where t is equal to 1 over a. That divides this interval up, t greater than or equal to 0, into 2 subintervals. And I have to figure out the sign of the velocity in those 2 intervals. Well, let me take a look at this for a minute. This is always positive. So the sign depends upon the sign of v of t, depends only upon this expression. I'm going to just take a look for a second at a times t. Well, let's see. If I take t, whoops, I'm sorry, a little tricky to write over there, Curtis, I apologize. If I take t less than 1 over a, what is a times t going to be like? Well, let's see. That means that a times t would be less than a times 1 over a, which would be less than 1. So this expression would be less than 1. So 1 minus that is going to be, well, positive. So v of t is positive in that interval. Similarly, I can show that the velocity is negative over here. And therefore, the particle is moving to the right in here, and then moving to the left in that interval from 1 over a on out. So when is the particle farthest to the right? Well, it's farthest to the right when t is equal to 1 over a. That's a sort of I think, a good multiple choice question. I didn't give you multiple choice possible answers there, but that's one I think you'd see on the multiple choice portion of the exam. Cool, Tom, should I do another one before I switch back? Or do you want to
yeah, or I could show something on this particular problem.
All right, that would be great. Okay, go ahead. I'll stop sharing on the board.
I'll try to keep it quick. Okay.
Go ahead. Go ahead.
All right, so I'm going to go back to the 84. This was for parametric. I did want to show something that people might, if they're using the 84 for parametric, something they may want to try. So I'm going to go to mode, and we probably spend 95% of our time in the function plotter, but we're going to go down here and change this to parametric. And then we'll go to our y equals menu, and we can see that this is where we can enter a pair of parametric expressions. So here I've got x1 of t. I've already got it set up as t times e to the negative a times t. But you'll notice that this was moving along the x-axis. So I really should set y1 t to equal to 0. However, I've set it equal to 1. We'll still be moving along a horizontal line, but the reason I did it is it lifts it off the axis. I think it just makes you able to see it better. So you just remember we're really talking about motion along the axis, and that's fine. Now this constant a, I will need to store a value in for that. Steve did it in full generality, but I'm going to go ahead and put in a particular value for a. So let me go quit to the calculator screen. And I'll tell you what, let me put in 0.5 and store that in for a. So I'll do alpha a. So I've stored a's 0.5. I think from what Steve said, we should get a motion where it goes furthest to the right. It'll be the rightmost point when t is equal to 1 over a, which would be 1 over 0.5 would be 2. So that's what we should expect from this motion. All right, let's take a look at the graph. And maybe we'll want a little bit better window. It's just showing me the completed graph here. Let me change my x-min to, let's say, negative 0.1, since it's always going to be positive, or non-negative, I should say. And I'll make this x-max 2. And graph it again. And now let me go ahead and trace this. And we can see that motion. It's moving to the right. And we should expect it to hit the rightmost point when t is equal to 2. Wow, we're getting awfully close, but it's slowing down. Now I'm looking at those x values, 0.72, 0.73, 734. At 2, it's 0.735. Steve was right. It should be starting to head to the left after this. So let me advance t one more time. Yep, it's starting to go back. In fact, it's always going to be, for t greater than 0, this, let's see, both t would be positive and this exponential expression will always be positive. So it's always going to be to the right of 0, and it's going to be approaching, oops, let me advance t. It'll approach y, excuse me, x equals 0, but it'll actually never reach there, okay? That'll be kind of a limiting value there. So that's what that looks like on the 84. Curtis, would this be a good time to take a look at that other thing real quickly, and then I'll turn it back to Steve? Okay. Just quickly, I think I know what Curtis was wanting to take a look at. Let me go back to mode and change this back to function. And let's enter that. I'll go back to the y equals. There's our integral expression. I think I saw in the chat that, you know, the comment how slowly this thing graphed. Mark Crowley suggested a way you could speed that up, and I did want to share that. If we go to the window settings, there's one that's seldom played with, but that XRes down here, this is, if you make that greater than 1, let's say you set that to 3, it's going to plot every third pixel instead of every single pixel across the screen. So it's going to go 3 times faster, and it'll connect the dots, so you'll still get this nice connected graph. Let's see how fast this graphs. Oh, I should have set my window back to what it was before. Let's do a zoom decimal here. Here we go. Oh, you know what? That set the res back again. So let me
break that. Yeah, press on and There you go.
Yeah, it's my XRES got set back to 1. So I'll set it back to 3. And after this little hiccup here, we should see a much faster graph. But we really don't see too much degradation in the quality.
Yeah.
I think it still looks
Quality
pretty
still looks
decent.
pretty good.
So, yeah, and it was much quicker.
Yeah.
So that's a way,
So-
especially for definite integral function graphs, that's something you may want to, that's a trick you may want to use to speed up the graphing.
So
All right.
Tom, my mistake
Steve,
earlier was that when you typed this in, you were still in function mode. And so that T that you were getting, you had to do alpha T to get the T in your equation.
Oh, yes, I did. Yeah.
Hmm.
And in fact, I could have used, let me go back to y equals. You know, I could have actually used X here,
Sure.
just done my independent variable key. But, you know, there's a part of me that feels that's bad form to use the same variable for the variable of integration as you're using for your independent variable
As your
here. So
boundaries, yeah.
yeah, so that's why, you know, you can get away with using X both places, even though that's not the best of form for what we would do with paper
Sure.
and pencil.
So you chose the T.
But yes, I did
arbitrarily
did
there. Okay.
use an alpha T to get that.
Okay. Perfect.
Steve, I'll give it back to you. Do you want to
Tom,
just grab
before
it, or?
Before you leave
Yeah,
that screen, I have one quick
Sure.
question for you. So on the screen where the lower bound on that definite integral is 1, if we wanted to make this just a little more complicated and make that lower bound a function of X, would the TI-84 also handle that? Although slowly, perhaps.
Well, we've got the res set at 3.
Okay.
What would you like to put down there, Steve?
Well, let's try something just for the heck of it, like 2X.
There it is.
All right, let's see if that works.
And let's graph it and see what happens.
Not a darn thing. Well, it could be off the screen. Oh, how about that? Interesting.
That sounds like an interesting exploration. We'll have to take that one and try it. Maybe come back with that.
Yeah, that's one that I think to play with
On a
I
later
think,
date.
because there may be
Okay.
something with that particular integrand.
Yes,
that
I think so.
We're getting a
Yeah.
behavior that's doing something weird here.
Yeah.
So.
But theoretically,
Okay,
it could
yeah.
do it, right? Theoretically, it could work. Yeah.
I would
should,
think
it
so.
really should,
I
yeah.
would think so.
Yeah. Okay. Well, that's good.
Because all it's doing is taking the value of X that's wanting to plot a point for, plugging that in,
Yeah.
computing the definite integral,
Yep.
and plotting that number.
Sure.
But I think we probably hit some value of X where we got a really strange integral of some
Yeah,
sort.
Okay.
And you know, your integrand does have an asymptote, so there might have been.
Oh, that's what it is. It's a minus
Some-
1. Yeah. Perhaps a
Yeah.
minus 1.
So
Yeah.
I think that's what it hit. Yeah.
Yep.
Yeah. Okay.
Okay. All right.
So
Very
So
good.
are you able to just grab control, Steve? 'Cause,
I'm going to try. How
I was
about
having
that?
trouble just getting.
Did that work, Curtis?
Yes, you look like you got it.
Let me see. I still see that we're seeing Tom's. Hold on. I've got Steve's
Okay.
showing on mine.
Beautiful.
Tom, do you see Steve's?
Let's see.
Yep, we got it. I think
Okay.
we're good.
All right.
Got it.
Real quick,
Okay. Great.
while we stopped there before Steve starts talking, I just want to put in one little quick plug, and that is that every time we do this, we also are offering a PDF certificate that you can go and download. If you want to email me, I'll put my email in the chat. And you can get that 1 hour of credit. I know that a lot of folks, that's a thing to be able to get a hold of. So let me know. My email is curtis@ti.com. So shoot me an email and I'll get you a link for downloading that certificate.
All right. For those of you who have done area volume problems already, I think this is a great problem to start out your class with tomorrow morning. This is a good review problem. Typical free response question. Almost. There's a little twist in here. So let's let R be the region bounded by these two graphs, y equal to sine of pi over 2x and y equal x squared minus 2x between 0 and 2. So I've taken the liberty here of providing these two graphs. The green graph is the parabola that opens up. So this is y equal x squared minus, minus 2x. And the blue graph over here, that's this trig graph. That's y equal to sine of pi over 2x. So the region R is bounded by those two graphs between 0 and 2. One thing I noticed right off the bat here, I'm going to draw in a sort of dashed line. There is a lot of symmetry here. Okay, and I'm going to make use of that symmetry as I solve this problem. So one of the first things I want to do is find the area of this region R. Now, the way that I teach this is that I ask my students to find what I call the upper curve of the high curve and the low curve. And I ask them, you know, there should be a definite integral from 0 to 2 of y high minus y low. The high curve is the sine curve. The low curve is the graph of this parabola. And so this would be the integral from 0 to 2. There's the high curve minus the low curve. Now, look, don't panic. We have worked out a very, I think, fair system that if a student puts y low minus y high in there and they arrive at a negative answer and they correct that, we give them full credit. In fact, I think we're aware that some teachers actually explain to their students, look, who cares what the high curve is and what the low curve is? Just do the definite integral of one minus the other. And if you get a negative answer, well, all right, the real answer is positive. Well, I don't think that's a good approach. I mean, it is a way to do it, but I don't think that's the best approach. So here's what I did. I made use of the symmetry. I can see there's a 2 out in front here, so I now went 0 to 1. And I think I can find the antiderivative of this expression term by term. Look, there's a u substitution in here, but we're all getting good enough at this. We're all beyond that, I think, in instruction. That's almost an integration by inspection. So there's a minus 2 over pi out in front, cosine term in there, minus x cubed over 3 plus x squared. There's still the 2 out in front because of symmetry. I've got to evaluate this at 0 and 1 and do a little bit of subtraction. So I did all of that and did a little bit of simplification here. Let's see what's going on if I've got this right here. I got a lot of zeros here. Let's see, the cosine of 0 is 1. So there's going to be a plus 2 over pi there. This is 0. Let's see if I combine those two terms. I've got a 2/3 and I did a little bit of simplification. And that's pretty neat. What's absolutely amazing to me, I don't know if Tom will have the opportunity to do this, but what is absolutely amazing to me is that you can use a computer algebra system and get this exact symbolic answer. Now, I'm not done here, and Curtis, there'll be some questions for the chat here in this next one. So let's use those same two curves, and let's see if we can find the volume of the solid obtained by rotating this region R about the line y equal 2. Now, often on the AP free response portion of the exam, we'll have a question like this that says set up but do not evaluate. But heck, we're going to evaluate this one, all right? So I want to take this region, if I can draw this, and I want to revolve it around that axis and find the volume of the resulting solid. Now, the way that I solve these, I wish I had more time to go into this, but the way that I solve these is I draw in two straight lines, one representing the outer radius. This has got to be washers because the axis is not a bounding curve. So I'm going to draw in one line from the axis of revolution to the outer curve, one straight line from the axis of revolution to the inner curve. Here's my outer radius and my inner radius. Now, what I notice in the way that I do these is I notice that those radii are perpendicular to the x-axis. Yes, they're perpendicular to this line y equal 2, but they're perpendicular to the x-axis. And to me, that says that I have to integrate with respect to x. So I've got to find an expression here for this outer radius and one for the inner radius. What's the distance? At an arbitrary point here, what's the distance from here to here? Well, I subtract. It would be 2 minus this value of y, which would be x squared minus 2x. We're using the washer method here. So pi times the expression r sub o squared minus r sub I squared. The inner radius, again, this distance, 2 minus, well, all right, at an arbitrary point x, that point, that value y would be the sine of pi over 2x. So the inner radius is 2 minus the sine of pi over 2x, quantity squared. You'll notice I have a 2 out in front here, and that's because, once again, I'm making use of symmetry. And holy Toledo, there's 3 dots in here. There's an awful lot going on. So a question for the chat is, and one for your students tomorrow morning is, can you get this exact symbolic answer without going to technology? How would you do that? How would you solve that one? How would you find an antiderivative? Maybe somebody can give us a quick idea of what they would do in the chat. And here's one more associated with this problem, this setup. In these area volume problems on the AP exam, often there's a part where we have this solid such that the base of a solid is a region R. And so for my particular region, the cross sections perpendicular to the x-axis are squares. I've done my best to sort of draw one of these cross sections. You can kind of see the square coming up from that region R in the plane. Well, okay, how do you do this one? You have to find an expression at an arbitrary point x in that region. We have to find an expression to the area of that cross section. Well, let's see. If I could find this distance, I know the area of a square is s squared. What's that distance? It would be this minus this. So let's see, it would be the sine of pi over 2x minus this value of y at that x, x squared minus 2x. That's the length of a side, and I've got to square it. All right, I'm going to put all this together. I'm going to make use of symmetry once again. There's a 2 out here, so I'm going 0 to 1. And boy, how do you find an antiderivative of that one? That's another good question for the chat. Boy, that's an even better one. Ask this one of your students tomorrow morning. See if they can get this one. I believe the exact symbolic answer of this is this, and this is really interesting. It's got a 30, 31, and a 32 in it. And it's
pi cubed.
And a pi cubed. How do you like that? As an aside, one common error in these types of problems is that, remember that in order to find the volume of this solid, we integrate from A to B of an expression for the area of a cross section. And the area of that cross section does not necessarily involve pi. It doesn't necessarily involve the square root of 3 over 2. And sometimes students see these problems, and under the pressure of a high stakes exam, they want to throw in a pi in there somewhere. Not necessarily. So cool. Tom, anything you want to try here? Or should I try to take a quick look at number 5?
I think he said, why don't you go ahead and take a look at number 5?
All right, I will indeed. Here we go. So number 4 is one that I made up for tonight's show. Number 5 was on the AP Facebook page, posted there by Ben Gazy, I believe. So the graph of a function f is shown in this figure. It has a semicircle and 3 straight lines. Very typical AP calculus question. This is a great one, great review question. G of x is, again, a function defined as a definite integral. There's my graph of f. Find g of 0 and g prime of 0. Well, all right, moving through this one kind of quickly. G of 0, looking at the definition, the integral from -3 to 0 of f of t dt. How am I going to do this one? Well, I've got to find this answer by using an area argument. I'm going to scribble a little bit up here. -3 to 0, I've got to find the area of that region. I suppose that's a trapezoid, but I split it up into the area down here, which is 3 squares, and the area of a triangle up above, and I got 9 halves. And the fundamental theorem of calculus comes into play here. We know that G prime, whoops, I'm sorry about that one. We know that G prime of X in this case is equal to F of X. That upper bound, if I can sneak back up here, is just X. It's not a function of X. So G prime of 0 is just F of 0. So I'm going to look on this graph. F of 0 is 1. That's pretty easy. That's pretty straightforward. B, find all the values at which G attains a relative maximum and justify your answer. Well, first I'm going to find all those places where the derivative of G is equal to 0. I know the derivative of G is F, so I've got to find all those places where F is 0. Are there any? Yes, there are. Here's one, and here's one. Are there any places where the derivative of G does not exist? No. I can see that F is defined everywhere on this interval, -5 to 4. There is a tendency to look at these places where there are sharp edges or corners on the graph of F, but that's okay. That has to do with the derivative of F, not the derivative of G. So I just have to check, are there any relative maxes at -4, 1, and 3? Well, let's see. If this is the derivative of G, G is decreasing and then increasing. So there's going to be a relative min there. G is increasing and increasing some more over here. There's nothing going on there at 1. It's increasing and then decreasing. So there's a relative max at X equal 3. Good problem. Now, don't panic, Curtis. There's an awful lot on this next page, but we'll get through this quickly. Find the absolute minimum value of G on this closed interval and justify your answer. Well, I would recommend in these types of problems that you use the table of values method or the candidates test, more commonly called perhaps the candidates test. So I have to find the value of G of X at each endpoint on the closed interval and at each critical value in the open interval. Well, from the previous part, I already know what the critical values are. They're -4, 1, and 3. The endpoints are -5 and 4. So here's my candidates test. I won't go through all of this with you, but I found all of these values with area arguments. It took me a little time, but I was able to do it. I would just caution you here. This is a little tricky. I've got to find the area down there and down there. So how do you do that? Think about that.
I'd use geometry.
Got to use geometry for sure, Curtis. Excellent. We've got to think about the area of a circle, subtract off. There's an area of a square in there.
Yeah.
Excellent. Excellent. So I did a lot of that. I've got all my values in here. I'm looking for an absolute minimum. And I think with a little bit of examination here, I can see that this value is greater than 0. Let's see, what's pi over 2? About 1.57. That's greater than 0. That's greater than 0. That's 0. So I have one negative value in this table. And so there's my absolute minimum value. It is -1. And it occurs when X is equal to -4.
So Steve, real quick, you are going to send me these slides so folks have access to this, right? So that's a good thing for folks to remember that we are doing that.
We post all of these. Yep.
I do have one question. I know you're probably not quite done. I do have one question that came in. It was back when you were asking, have your students look at these two problems from the last one a moment ago, and there was a question about, or at least a comment about the students kind of getting intimidated when they have to use distributive property significantly. Do you have any suggestions or things that you could, you might do to maybe help eliminate or at least
if you're talking about the distributive property here,
getting the distributive property taken care of,
or multiplying everything out
dealing with that.
Boy, I don't know. I guess
I have a quick suggestion.
Okay, shoot.
So on these, you're given these two functions, and there's nothing wrong at all with the student actually naming those functions. Like they could say, hey, I'm going to say f of x is equal to this sine of pi over 2 times x. and I'm going to call g of x the x squared minus 2x. And once they've declared that, they can just refer to those.
Oh, yeah.
And on
Okay.
these problems, I'm almost sure these would be on the calculator active part of the exam.
Absolutely.
And
wouldn't
then
be
if you've got the
expected to
CAS
do that.
machine, you can kind of do things from a computer.
And you don't need a CAS machine here. I mean, you just do a numerical integral, but you could say just f of x minus g of x quantity squared.
Yep.
And as long as you clearly labeled those as your two functions. Similarly, if you're actually using the calculator to do the calculation, I would suggest storing these two functions on the 84, for example, as y1 and y2.
Yeah.
And then when you're doing your calculations, use those references rather than re-entering these on part A, part B, part C. You're just asking to make a typo when you're typing it in. So.
Yeah.
Sure.
All right, one last one, Curtis, and we'll call it a night. This had an interesting sort of conclusion, I think. So part D here, where is it? Here it is. Find all the values of x in the open interval at which the graph of G has a point of inflection. Well, what we need to do is we need to find places where G prime of x changes from increasing to decreasing or vice versa. So we have a graph of f, which is the graph of G prime. And notice that it does change here from increasing to decreasing right there. So we're going to have a point of inflection at x equal minus 3. It sneaks down here. It's still decreasing, but it changes right here from decreasing to increasing. And then it changes again right there from increasing to decreasing. So it certainly looks like we have 3 points of inflection on the graph of G. And you know me, I want to try to back this up. And I was able to, again, actually sketch the graph of G using a method that Tom described at the very beginning of the hour. And if you look carefully, you can really see these points of inflection. You can see that the graph is concave up here. A little tricky to see, but it's concave down, concave up here, and concave down again. There are indeed 3 points of inflection. So great. Thank you, Curtis. That's all I got for tonight. Some nice problems posted. Hope we answered a couple of questions.
Yeah, I think so. And so we were looking through the chat just a little bit ago, and I'm going to have Stephen Beck. I think he's joining us from Florida, someplace down in your neck of the woods there.
Okay.
Steve.
Well, I could go to his classroom then, maybe.
So, Stephen Beck, if you want to email me, Curtis at TI.com, we'll get the ball rolling as far as getting a session set up for you and Steve Kokoska in here and Tom Dick to have that session rolling. I also want to point out that, again, that if you want to email me, anyone who's been watching this evening or watches this one after we've done it live, you can email me and I will send you a link to download a certificate for having participated. Lastly, I want to just point out that our next session is going to be on a very special math day that we all love to celebrate. We'll be celebrating Monday night calculus. We'll have a special one on Pi Day. Will be our next session, March 14th. We'll look forward to seeing that. And let me answer this one question, or I'll have Steve or Tom answer this question. Bernard just posted in. He was the one who posted that last question. Do you have to do all of the multiple steps to find the exact values for the absolute minimum? Since it is clear after x equals -4, the function accumulates and is positive.
So you wouldn't, my response to that is, on the AP exam, you would not necessarily have to compute all of those values, but you would have to put something on the paper that explains why you eliminated them. So
Okay.
convincing argument as to why you're not computing those.
Would the justification of, since it's clear that after x equals 4, the function is accumulating and is positive, be enough, or do I have to give a little bit more justification there, Steve?
A tough one. Depends on who the chief reader is.
Wouldn't fly in your book based on the way I saw you kind of.
Perhaps not.
Okay. Well, that's good. I appreciate that, Steve. So hopefully that answers your question, Bernard. At this point, I think we can call it a night. So I really appreciate once again, Steve, Tom, you guys, thank you so much for giving your time and your expertise. And I'll be in contact with you as far as setting up this next session.
Sounds good. Thanks, Curtis.
All right, great. Thanks, everybody.